for your kind introduction. I think I am audible to all. There is some background noise, but everyone can hear me, right?
I can
Properly?
hear. Uh,
Yes, yes, you are audible.
Okay. Okay. Thank you for also for giving me the opportunity to give this talk. So some before I start, just give you some statutory disclaimer that the most of the content that you will find in this talk are already available in the public domain. Unfortunately, I haven't cited all because it was not possible to cite all the things that I have copied from those publicly available uh, documents or slides or something like that. And secondly, some pictures or plots you may not find very scientifically accurate because they were made for demonstration purposes only. So having said that, let me then proceed towards what I want to talk about today on this in this talk. So before I go to the particle identification that uh, we are doing right now in these ALICE, CBM, STAR, all these international mega projects, I think it is also relevant to give some bit of history about this PID, which was done by the affiliates of this institute, which is hosting this Alice India meeting, Professor D.M. Bose and Professor Bipa Chowdhury. They did a great deal of pioneering work in characterizing the cosmic rays back in beginning of the 19th century or the middle half of 19th century using photographic emulsion techniques. Those days, all these detectors which we see in these experiments in Alice Star same were not available. So they use these photographic emulsion techniques to characterize the cosmic ray shower, and apparently they found the evidence of a new meson candidate, which was later identified as pi. So having this said that this the particle identification work is not new. It has been going since very long, and a lot of pioneering work has been done by the scientists, not only in India and obviously across the world. So now, since giving with this history in hand, let's move on to our motivation for doing the particle identification in the perspective of heavy ion physics. So I will just very briefly tell you about why we are very so much willing to do the PID. So just compare the plots you have on the left and the right hand side. So the plots in the left hand side, it gives it is about the V2 and RAA of charged particles. I'm not going to explain you about the V2 and RAA because I presume you already know what are these quantities. And then contrast them with the plot on the right side, which is also the same quantity, that is the V2 and RAA, but it is for the identified particles. There are a lot of particles which are for which this V2 and RA is calculated. And I think you would appreciate the fact that the moment you introduce the PID, the moment your detectors are capable of rendering PID, you get a wealth of information and new insights. You see a lot of new novel structures in these the plot which has PID in it. You see, isn't it? That when you have a charged particle, the V2 as a function of the transverse momentum, you see there is a rise with PT and some kind of fall. And the similar thing for RAA, which you see a suppression as a function of PT. And the moment you bring in the particle identification in the picture, you start seeing a lot of different structures coming up. You see there is some kind of ordering that some at different PTs, and also you can see with both V2 and RAA. So the current motivation for doing the PITs is that you you get more insight, more information, you extract more information about quark-gluon plasma, which we are which we are studying through the heavy ion physics. So having said that, let's move to the thing that how to do the particle identification. So, so in this talk, I will just give the general scheme of doing particle identification without going into very details, because you know the details depend upon the experiments or the physics analysis that you are intended to do. So this is a very schematic and very basic, rudimentary and general overview of how you can extract the information related to particle identification. So what are these? So mostly when you do the PID, you have two sets of particle. One is the stable particle, which has a very large lifetime, which you can actually intercept in the detectors. And another is the unstable particles, which decays immediately after they are produced, which whose signatures you cannot retrieve or extract directly from the detector. So for the stable charge particle, a direct way to do the identification is the determination of rest mass, isn't it? Means what we want to do for in the PID is that we want to find their mass, or at least we find some quantity which is relatable to mass. Now, all of us know that the when we design a high energy experiment, the first thing we try to measure, or at least it is a mandatory quantity to be measured, is the momentum. And if you know the momentum, if the momentum is known from your tracking devices or the tracking system, which is equivalent to a velocity, and for a given momentum, you can immediately say that the particle which has a lower mass has higher velocity, and the vice versa. So, what is the general strategy? The general strategy is to find, first of all, the momentum, and another quantity, which is essentially a detector response that depends on the velocity. So if you can find these two quantities simultaneously, you are done. Then you can relate them in some way or the other and try to determine the mass of the particle. So what are these ways? I have enlisted few, which are most commonly or frequently used in the high energy experiment is the energy loss. First is the energy loss. And I think already in the earlier lectures you have seen, or you have, or also you know from your previous knowledge, that the energy loss somehow depends on the beta as 1 by beta square. I will come to the details in the later slide. So here I will just introduce about how these the detector response are connected to mass via the velocity. Next is the time of flight, which is very much connected to the velocity as 1 by beta. And then there is something called the transition radiation, which is related to the boost factor of the particle. And you can easily calculate how gamma is related to the beta. And the Cherenkov emission, the Cherenkov radiation, that is when the particle velocity is higher than the velocity of light in a given medium, then the angle at which the Cherenkov light is emitted is inversely proportional to the refractive index, that is the n of the medium, refractive index of the medium times the beta, which is again the velocity. So you see all these four methods somehow relates to the velocity in some way or the other, or the beta of the particle in some way or the other. So these four methods are generally and frequently used in all the high energy physics experiments. And the next that is you done for the PID is the calorimetry. And I think previously Sanjeev has introduced that when you use the calorimeter, you kind of deposit the particles, deposit the entire energy it has. So these calorimeters are basically used for electron, photon, and hadron discrimination based on their shower profile. And the last but not the least are the unstable particles, which I was just telling you the moment earlier, that there are two class of particles: the stable, which we directly detect at the detector, and the unstable, which you that immediately detects. So you have to somehow retrace them back from what you detect. Means from the stable particles that are at your disposal, you have to get back those unstable particles via invariant mass reconstruction. And there you can use some topological cuts or topological means, uh, constraints in order to increase the signal over background. So these are the few basic layout for doing the particle identification. Now let us move to the details one by one. So before I go to the details, let me just introduce to you briefly that when you want to do PID, the positioning of the detectors are very important. Also, I remember in the detector class, Sanjeev, they introduced that there is a general scheme, there is a general way that your detector should be arranged. So there is a strategically these detectors are placed. Why? Because you don't want the performance of one detector to be hampered, or the one detector interfering with the another detector. So you want your detectors to be placed in such a way that you can extract the best out of them. So the general scheme or the general layout of positioning the detectors are that the trackers, which are generally low material budget detectors, are placed ahead, means they are placed close to the collision vertex or the collision point. Then you have the odd time of flight or TRD, whatever they are, which are also quote unquote low material budget detectors. Then they are placed after the tracker. And then comes the calorimeters, which have the high material budget. And also there is a kind of ordering for calorimeter. Generally, the electromagnetic calorimeters are placed first, and then the hadronic calorimeter. And almost at the end, you place the muon detectors, because you know the muons almost interact very weakly, and they just pass through, and that's so you can leave them to the until the end, and then you do the detection of the muons. And also about the coverage, the every all those who proposes the experiment or designs the experiment, their best wish is to design it cover the 4 pi solid angle across the collision vertex. But this is not always possible, because there are budget in the sense that your when you design or propose the experiment, you have to also keep in mind of the cost. So you have to kind of compromise or optimize, rather better to say optimize between your physics objective and the cost effectiveness. And this way you design your detector. Now, having told you about the general layout of the detectors, let me move to the details which I introduced in the earlier slide of how we do the PID. So first in the list is the ionization energy loss. So I think this has been taught to you several times in your classes and also in the current school. So the ionization energy loss is described by this Bethe block formula, which gives the amount of energy loss is amount depends on the inverse of the velocity, and also there is a complicated dependence on the gamma times beta. So if you see this one, you see this is the complete formula of the Bethe block, and you can do some kind of simplistic representation using the one in the left, which says that at first the amount of energy that the particle will lose will decrease with the beta, because it has a proportionality with 1 by beta square. And at this low momentum, at means from low, as you increase the momentum, there will be a decrease which follows this 1 by beta square pattern, and then it achieves a minimum, which is shown in the red dotted line here. And further, there is a relativistic rise, and so again the energy loss increases. So from this plot, you can see that the different particles lose different amount of energy when you plot them as a function of momentum. And this you can exploit actually to separate the different species from one another. Okay, so like if you concentrate at the low momentum, say below say 2 or 3 GeV, you can see a distinct line of kaon and pion. Of although these are very idealistic, means in reality you will not see so precise or so sharp lines, but you can see at low momentum, these pions, kaons, protons, they have a different amount of energy loss at a given momentum. So this you can actually exploit to separate the samples of pure samples of pions, kaons, and protons. And then it again drops with the momentum, and then it starts rising, which is the say for different particle, this rise starts from different values of momentum, but eventually they rise at and this rise is called the relativistic rise, where also you get some amount of some degree of separation between the particles, but not so sharp as it were when the momentum was low, maybe between zero point 0.5 to 2 GeV or something like that. So these informations, this energy loss information can be exploited to identify or separate out the particles. Now, one thing I think you have already noticed that this Bethe block formula is not applicable for electron. You see the electron behaves completely different for this ionization, this ddx in the ddx versus momentum curve. So can anyone tell why it is so? Okay. Uh, this is because this, first of all, this Bethe block formula is only applicable for heavier particles. And you know, the electron mass is very small. So the ionization loss for energy loss by electrons is almost insignificant. They mostly lose energy via Bremsstrahlung radiation. So the Bethe block formula is not very much applicable for the electrons. And so this is the quantity, the ddx, which you measure as a function of momentum. And the detectors that are basically used to do this is the silicon based or the drift chamber based detector, which also Shoikodda previously just told in the earlier class. So this is one kind of detector response that one can use to separate out the different particles. So this is a kind of a more realistic detector response, TPC-DEDX. TPC is a time projection chamber, which is there in the ALICE. So if you plot the TPC-DEDX versus momentum, you find this kind of curves where you can see there is first there are these the particles are well separated, and this then as the momentum increases, they collapse and start merging, and you lose the separability of each particles, means you can no longer distinguish these particles individually. So you can clearly see a contrast between the earlier and this plot, that in that plot there were this solid lines, is the very kind of idealistic plot where you see that they are all well very separated, distinctly separated. But when you apply to this policy to your experiment, you see that the life is not so simple, because there are several there's reasons that the TDX that you measure are affected. So there is a width in the distribution. So everything that you measure has a width, and that those widths changes with the momentum and several other factors. So you don't get such a precise DDX plot, and so you have a width, and nothing we can do. We have to live with this. So what we can do is that we can choose that part of the kinematics where the DDX can give you the best response. Now, let's move to the another concept of separating the particle. So the another concept is the time of flight. So what is the time of flight? As the name suggests, it is the time taken by a particle to cover from point A to point B. And you can calculate the time difference. So there, what you need two things. One is a start and another is a stop. And you have to know the relative separation between the 2 points where you do the start and where you ask for the stop. So in a, if you can visualize in the heavy ion experiment like this, so the TOF detector in Alice, and we actually, so if the when the collision happens, that is, you can, that if you can somehow register that time, that is the start time, because all the particles are produced. You assume at the collision moment from the particles are produced, and then it means this is a very simplistic view of a simplistic picture. And then from there, the particle flies to the top, which is located at a distant, at some distance, and there you get the stop signal. So you can measure the time of start, that is, you can say T0 or T1, and the time where it stops, which you call it T2, and the difference between that is related to the particle velocity. So in order to do this timing measurement, what you need is a very detectors that have a very good resolution, basically the timing resolution. Now this is something what is we call as the resolution. This is the sigma total, which includes the detector resolution. This sigma TOF and T0 is the detector resolution. Plus there is the resolution which is being added because of the electronics, and overall it contributes to the overall resolution of your measurement. So typically for Alice, if I'm not very wrong, for Alice TOF, the typical value of the resolution is around 50 picosecond. So with this resolution, you can determine, you can actually separate the particles in the most effective momentum range between 1 to 4 GeV. So how do you do that? How do you distinguish the particles at same momentum? You just see this formula. So this delta T, that is related to the difference in the velocities of the two particle. And as I have earlier told you, that if you measure the momentum, and at the same momentum, the heavier particle has heavier particle has lower velocity, and the lower particle has higher velocity. So using this concept directly, you can calculate the time difference, that is the time that say a pion or a kaon has taken to move from the start to the stop position, that is from the collision vertex till till they are detected at the time of flight detector at some distance. So what you measure for the time of flight is a TOF beta, and you plot against the momentum. So if you remember, the even for the earlier case, we were measuring the detector signal, that is the DDX, and plotting it as against the momentum. So the same strategy we follow here. So we extract the TOF beta and we plot it as a function of momentum, and you see the distinct bands of the different particles. So you can exploit, or you can use this information to separate out the particles from one another. So with this information, let me give you some very tiny take-home problem. So the problem is that is it possible to separate pions and kaons with the TOF detector that have a total resolution, means this one, sigma total of around 80 picosecond at the momentum of 1 GeV by C. So you can use this formula to calculate whether it is doable or not, and you can take the L value as the Alice TOF distance from the vertex, that is the radial position. And also you can try to find out what is the limiting momentum beyond which the pions and kaons cannot be distinguished. So these two are take-home problems for you. Can try to solve and then email me. My email address is given in the first slide. You have to use this formula in a different way. I think you already been taught about this from your in the relativistic class. So relativistic kinematic class. So you just use this formula. You have to do some jugglery with the relativistic kinematical algebra, and you can easily calculate what is the, whether you can detect or whether you can separate pions and kaons with these kind of resolutions and at momentum 1 GeV. And you just, as a sake of simplicity, you just take the L equals to the list of radial position. And also then you can find some limiting momentum value beyond which you can no longer separate these pions and kaons. Okay, so let me move to the another quantity that is used, also used for this particle identification. So that this quantity is called the transition radiation. So what is this transition radiation? So transition radiations, these radiations are emitted when the relativistic charge particles crosses the junction of two medium or two media that has different dielectric constant. So if you have one media with a say dielectric constant epsilon 1 and another media with a dielectric constant epsilon 2, so when a charge particle passes through this media, it emits radiation. And this radiation, this transition radiation, can be actually used to construct the transition radiation detectors. So, and this transition radiation detector can be very much helpful in for doing the particle identification. So now some characteristics of this, the energy or the photon that is radiated is all, it depends on the boost factor gamma. So so if you remember, I told you that in the first say in the few slides earlier, that we have to somehow find the quantity of the detector response that is related to the beta. So in the first ionization energy loss, the DDX is related to some way with beta square and the log of beta gamma. The time of flight is also related to 1 by beta. And again, the energy that is radiated by this transition radiation is also related to gamma, which is which you obviously know that is also related to beta. And there is a gamma. So this so a lot of the R&D were done to determine what should be the appropriate value of gamma, or the critical value of gamma beyond which you start to get a significant amount of the photons, or the energy of photons is quite significant, so that that can be converted into a sizable or a detectable signal. And it was found that beyond the gamma threshold of 1000, actually you get a significant amount of energy deposition. So if you in transition radiation detectors, it is a combination of two energy loss. One is the energy loss, the specific energy loss, which is like ionization energy loss, which I discussed few slides earlier, and the other is the energy loss from the transition photons. The photons which are radiated out of this charge particle, they again interact with the medium and lose energy. So it is the combination of the both DEDX ionization and DEDX from the transition gamma. So when this adds up, you see for pions and electrons, you see a distinct difference, that the pions have less total DEDX, whereas the electrons have higher total DEDX. And this can be used to separate out the electrons from pions. So this is from again from the real experimental scenario. It is the total TRD DDX, and you can see a more or less distinct band of pion, which is lying below an electron band. So using TRD actually gives a very good and efficient electron pion discrimination. So when you cannot distinguish between when you have, say, ionization energy loss from ionization energy loss, if it is not possible for you to use using the ionization energy loss information, if it is not possible to separate electron pion, then you come to time of flight. Even if it is not possible there, then you come to this TRD, and you see and using TRD information, you can separate out the electrons from pions. Next, we come to another set of another type of radiation, which is the Cherenkov radiation. I think this thing you have also read in your post graduation classes, also in the electromagnetic courses, also. That is that when the particle, when the relative traverses through a medium with a velocity that is faster than the velocity of light in that medium, it emits Cherenkov photon. And this Cherenkov photon, the angle at which these Cherenkov photons are emitted are related to the are inversely related to the refractive index of the medium and the particle velocity in that medium. Now, these Cherenkov photons, if these Cherenkov photons can be collected on a position sensitive photosensitive position detectors, you can actually construct this type of rings from the Cherenkov radiation. And as you see, this the angle it intercepts is depends on the beta. So you can clearly say that if your particle has a lower value of beta, that you will have Cherenkov radiation, which has a larger angle, larger theta. And if your beta value is small, that is, if the particle is massive for the same momentum, you will have the Cherenkov angle, which is which is sorry, I think I said the opposite. Then if your beta value is small, that is, if your then your Cherenkov angle will be large, and if the beta value is large, your Cherenkov angle will be small. So you can see a particular demonstration of this in the lower plot, where you can see that the protons and pions for a very these are the results for a very ideal case. You see that the Cherenkov angles for when you plot this cos theta, this Cherenkov angle, you see there is a distinct separation between pions and protons, because they are at same momentum, they are related by inverse of 1 by beta. Similarly, when you extract these signals from the real detectors like high momentum particle identification detector in Alice, there you also see the similar behavior. That is the variation of the Cherenkov angle with the momentum. There is all the particles are distinctly, means at least quite reasonably separated out up to certain values of momentum. So, till now, what we have discussed, or what I have tried to tell you, is that once you know the momentum, you have to find out another detector response or detector signal that is somehow related to the velocity of the particle, and then combining these two pairs of information, you can actually separate out the particles. So with this, I kind of conclude the first part of the particle identification, where we mostly relied on the measurement of momentum, and somehow the measurement of or the detector responses that were related to the velocity of the particle, that is the ionization, time of flight, transition radiation, and the Cherenkov radiation. So next I will go to another part. So before that, I want to ask you if you have any doubts, queries, or clarification to be made. Should I proceed? Or if you have something to ask? Okay, so I presume that there is no question for me. So next, move to calorimetry. So as I told in the first slide, that there will be mainly three ways of doing this particular identification. First was from the based on the information of momentum and another information that depends on the velocity. Next is the calorimetry. So in most of the high energy physics experiments, you use two kinds of calorimeter. One is the electromagnetic or EM calorimeter, and another is the hadronic calorimeter. So, so in the electromagnetic calorimeter, the electrons and photons develop the shower through the energy loss mechanism, mostly by Bremsstrahlung and pair production. Means the photons mostly interact by pair production, and electrons, because of their very light mass, they lose most of the energy by the Bremsstrahlung. And one of the feature of this electromagnetic shower is that this shower is generally very compact, means the transverse spread of the shower is not very wide, and it's also not it does the lateral spread of the shower is also very limited. So the shower in one sense, the shower is very compact and has a less depth. And for a particular material, say lead tungsten, I have given this one example for you to clearly understand. So it's the depth or the lateral spread of the shower is about 23 centimeter, whereas the transverse spread of the shower is like 2.1 centimeter or so. These are some rough values. And then comes the hadronic calorimeter. Now, hadronic calorimeter is something interesting. So when I think the Sanjeev also told you in the detector class that for hadronic calorimeter, the hadrons need to interact strongly with the nuclei, right? So when they interact, they actually produce mostly the hadrons like pions, like pi plus and pi minus and pi zeros. Now, these pi zeros, they immediately decay to 2 gamma, which again start developing the electromagnetic cascade. So, for hadronic calorimeter, actually you have two components of the shower. One is the hadronic component and another is the electromagnetic component. So, the hadronic showers are a bit complicated. It has a complicated structure. So the shower is generally broad and deep. The shower or the hadronic cascade that is developed in the hadronic calorimeter is very broad. The transverse spread is very wide, and also the depth means the length it propagates by the time it loses the almost all of its energy is also very large. So for a typical hadronic cascade made of iron, the lateral spread in the shower is like 80 centimeter, whereas the transverse spread is 16 centimeter. So you can clearly distinguish that the shower pattern, the shower formation has a difference for electromagnetic calorimeter and the hadronic calorimeter. So one can in some way exploit these differences in the shower profile to identify the particles. Now let's see how we can do this. So suppose we are doing the distinction between the electron and the photon. Okay, so electron is a charged particle and the photon is obviously is a neutral, charge neutral. So what will happen? So electron will mostly deposit all of its energy in the electromagnetic calorimeter. Similarly, the photon will also deposit entire energy, to lose entire energy in the electromagnetic calorimeter. But there is one distinctive feature that separate electron and photon. What is that? That is the electron will leave track in the tracker, but photon will not. So you can actually use this information to separate out the shower or the cluster in your electromagnetic calorimeter, which is from electron or from photon. You use the tracker information, you can actually separate out the electron from photon. So how you can actually do that? That was kind of a qualitative argument. So actually it is done? It is done in the way that you have a track in the in the tracker, and then you extrapolate the track in the calorimeter, and you try to see whether around this track if you have some cluster. And if you have some cluster, you try to calculate the residuals, that is the difference in the eta and the phi between the cluster and the track. And if those values are within some predefined limit, which this predefined limit actually you get by from simulation or doing the test beam. If they're within some predefined limit, then you can say, well, this cluster is from electron and this cluster is from photon. So this way you can actually separate out the electron and the photon cluster. Now, next come to the hadronic calorimeters. The hadronic calorimeters also have the similar feature. So what is that? The charge hadrons, it will propagate through the calorimeter. It will lose most of its energy in the hadronic calorimeter. But remember nothing stops it from losing a fraction or the part of energy in the electromagnetic calorimeter. So this actually makes this actually creates complication for distinction of for finding distinction of particle during the PID in electromagnetic calorimeter, because a hadron is also losing some fraction of its energy in the electromagnetic calorimeter, which can be misidentified as the energy deposited by electron. And also the charge hadron leaves track in the tracker. So in some way it may be misinterpreted as an electron candidate. For neutral hadron, it is similar to photon. It will not leave any track in the tracker, but it will lose most of its energy in the hadronic calorimeter. And similar to charge hadron, it will have some fraction of energy lost in the electromagnetic calorimeter. Now, as I say that since the hadrons lose a fraction of energy in the electromagnetic calorimeter, it creates complication for separating out the basically the electrons from hadrons. So how can you actually separate the electrons from hadrons in EM calorimeter? Because both electron and the charge hadrons, they lose, it means electrons lose the entire energy in the electromagnetic calorimeter, whereas charge hadron lose fraction of its energy in the calorimeter, but they can be very resembling, they can be very much identical. And also you cannot use the tracker information here because both electron and the charge hadron leaves tracks in the tracker. So you lose the distinctiveness or you cannot use the tracker as an additional separator for electron and hadron. So how you do this? How can one separate out the the cluster produced by electron from hadron? This is a simple way. So use the relativistic kinematics first. That is the energy and the momentum, the relation of the energy momentum. So E square is equals to P square plus M square. Now, under the assumption that momentum is lesser than much larger than the mass, you can assume that the mass of energy deposited by electron is almost equal to the proton, is almost equal to the momentum. So if you plot E by P ratio for the electrons, you see that you get a nice Gaussian peak around 1. Whereas when you do the same for the pions, you see that the value is shifted much away from the 1. So you can use this E by P ratio as an additional discriminator to separate out the cluster which is produced by electron and the cluster that is produced by a hadron. So this way one can actually use the calorimetric information to do the particle to do basically the electron photon discrimination and also the electron hadron discrimination. Obviously you will not know the particular kind of hadron, particular type of hadron, but you can broadly say that this is electron and this is a non-electron candidate or a hadronic candidate. Now, again, I give you some kind of homework that now now we have been considering several cases, right? Electron, photon, then electron and charged hadron. Now you consider a case like photon and the neutral hadron. So again, the scenario is that you cannot use tracker anymore because the photon and both photon and neutral hadron leaves no trace in tracker. Only you can have the information is that they are the energy that they deposit in the electromagnetic calorimeter. So using this, just the information from the electromagnetic and the hadronic calorimeters, how can you at least qualitatively separate out the photon and the neutral hadron? So this is kind of homework for you. You can either tell me in the next class, or you can also email me with your solutions. So now I come to the last part of my talk, which is basically the detection of the unstable particles. So what is that? So as I told you in the very beginning, that the most of the particles that you know are not stable. Only the stable particles are the pions, kaons, then protons, muons, and electrons. Quite a large number of particles are unstable, and they decay almost immediately after they are produced. Now, how do you know about those particles? How you detect those particles? So what you have to do for detecting those particles is that you have to reconstruct those back from your decay daughters. If you know they are decay daughter candidate, then you can use the invariant mass formula, which I have written here, and also by now from your relativistic kinematic class, that if you know the form momentum of the decay daughters, then you can actually retrieve or get back the mother particle from which these daughters have originated. So I have just given one or two examples for here, is that for phi mesons which decay into kaons. So if you uh, so basically there are two ways of doing this. Roughly, you take that the phi is a neutral meson, so it will always decay into two. It will have two decay daughters of unlike charges. So you take two unlike charges track, any two unlike charges track, then assume from since you take any two unlike charges track, you already know their momentum, at least three momentum Now you assume a Keon mass hypothesis. You tell that, okay, all those tracks are Keon. Let me assume all those tracks are Keons. And you, using the Keon mass hypothesis, you calculate their energy. So you have the tree momentum from the tracker, and you have the fourth component, that is the energy from the mass hypothesis. And then you do this invariant mass reconstruction. You will get some peak over a very large background. Now, how can you reduce the background? Now you use the PID on your decay daughters. You do the pairing of only those tracks which you can identify as kaons by using the other detector informations. And when you do that, then you will see there will be a significant suppression in the background. So by this way, you actually can get a very good signal over background. Similarly for pi zero, which is kind of means uh, very popular, means which kind of frequently you reconstructed back from the gammas. So the pi zeros decays into two photons, and those two photons, you from those two photons, you can actually reconstruct it back to the pi zeros. Now you can have a lot of photons, right? The photons are emitted throughout the QGP evolution, and both the phases, both the partonic and the hadronic phases of the QGP of the heavy-ion collision. So there are a lot of photons. So if you just take two photons and then start pairing them, I think you will get nothing, because the signal over the background will be so overwhelming that your signal will be lost. Now, how you can improve the signal by background? So again, you go to the electromagnetic EMCAL. You look at the EMCAL cluster. Since you know that the pi zeros are, say, with some momentum, they are boosted and they will decay into the photon. So in the EMCAL, you can find two clusters which are which are rather close to each other. So you can use the shower profiles to manipulate the pairing condition. Okay, so just means not just with just if you do not just on an ad hoc basis take two clusters, if you use some additional constraint that I will take those two clusters which have some spatial proximity, then do the invariant mass reconstruction, you will have a better signal over background ratio. So this reconstructing these unstable particles, that is the particles which decays immediately after production, using the information that their daughter candidates lives in the detector, you can actually gain in the signal over background ratio. Now, there is another type of decays, means there are some particles uh, their decay lifetime is relatively larger. That is, they do not decay almost immediately after they are produced. So for those, actually, you can use some other topological, what is the jargon for this is that you can use some topological informations to gain of to get a better signal over background ratio. Like I have demonstrated here for the D meson. So D meson has a typical means the it its lifetime is bit larger, and the decay length is like about 123 micrometers. So from primary vertex, the D meson will be produced at the primary vertex, then it will travel a length of around 120 micrometer, and then it will decay at the secondary vertex. So this is the primary vertex where it is produced. It travels this length, and then it decays here, secondary vertex. And from there, its daughter candidates flies off. So based on this kind of topology, you see this looks like a V. So sometimes, loosely speaking, these are also called V candidates. So these topologies can be exploited to actually to get more significance in your in the signal by background ratios. So what you can do, we can construct is like you can have quantities like, sorry, there is some background noise. Okay. So basically, you can use these decay topologies to get a better signal over background ratio. What quantities you can construct is like you can have this difference between the primary and the secondary vertex, which is constrained by the lifetime of the particle. Then you can calculate the closest approach of the decay daughter to the secondary vertex, and also you can calculate the distance between the secondary the decay daughters with respect to the primary vertex, and also this cosine pointing angle A, or cosine of the pointing angle. All these topological constraints you can apply on the decay candidates to reconstruct your mother particles. And if you, besides the normal invariant mass reconstruction, if you apply these topological cards, you will get more enhancement in your signal and a better signal by background ratios. So these are some kind of general picture of the particle identification scheme that is generally followed in the high energy experiment. So in for this class, I will stop here. If you have more questions, comments, queries, anything, you can start asking.
Hello, sir.
Yes,
I have a question
yes,
and
please
that
go ahead.
in time of flight detector,
Mm-hmm.
actually we are in case of time of flight detector,
Yes.
actually we are calculating the time taken for the flight
Mm-hmm.
uh, from the velocities,
Yes.
and there are a lots of undetected particles going
Mm-hmm.
to the time of flight detector, and so
What
there
do you
would
mean
be
by
some.
undetected particle?
Actually, the particles, pion ions and protons, maybe, and so all other particles, we have to detect them with
Mm-hmm.
respect to their velocities, actually.
Mm-hmm.
And
Yes.
so my question is that there would be some scenario that the velocity of pion
Mm-hmm.
with having some momentum
Mm-hmm.
maybe merged with the velocity of some other particles, say let's say
No, of
chiron,
course. Yes,
with
that's why you
another
see the.
some momentum, having some
Yes.
another momentum.
Yes, of course.
And
This can happen.
My question is that how can we distinguish or separate between these with these velocities with pion and other particle, let's say cation or proton, actually.
Means you mean to say when they are marching, how can you separate?
Yes, yes, yes.
Okay, so of course, when you're like, if you see this beta top beta versus momentum curve, of course, at certain values of after certain values of momentum, they start to collapse. So there you do not have a direct approach of measuring them. You have to use a combined approach. What is that? You have to choose another detector in that momentum range which has a better separation for those species. Suppose let's take an example. Suppose you use uh, TPC or DDX information in at 1 GV. Okay, so you can see that 1 GV or one between 1 to 2 GV, your pion and kaon collapses. The signal from pion and kaon are almost identical, right? Now you
Yes.
go to top. When you go to top, you see a better separation between pion and kaon. So what you do the combined PID approach. You take two or maybe multiple detectors such that they give a complementary information. If you do not have a better separation in one detector, you use another detector so that you can add to the distinctiveness of the separation using the another detector. So in this way, using the combined PID approach, actually you can separate between the two species which you want intend to separate. This is one way. Then there is another way. It is called the statistical separation. A statistical way of finding where which is which you cannot do on a track by track basis. What you have to do, you have to have some a priori knowledge of your detector response from Monte Carlos. I will discuss this in the next class. So based on this a priori knowledge, if you project your signal at a given momentum, then you can actually calculate what fraction of your signal is from pion, what fraction is from kaon, and what fraction is from proton. So this is a kind of statistical approach. It is not applicable on a track by track basis. Does it answer your question or?
Yes, yes, yes. I'm actually just thank you, sir.
Okay. Anything you means if you think I'm not clear to you, you can write me an email. I will try to explain.
Okay, sir. Okay.
Okay, thank you.
Thank you, sir.
Any more question I'm expecting? Okay. Shoykot da?
Yes, Subikash. So